What happens if you have a complex number, say z2, which is 2 minus I, and you multiply it by a scalar? Let's have a look what happens on the plane. So if we put z2 here, it's 2 across to the right and 1 down. If I multiply this by a half, okay, let's do it algebraically. We get a half 2 minus I. A half times 2 is just 1. A half times minus I is just minus a half I. If I plot it in, I go 1 across, a half down. If I do minus 2 times z2, I'll get algebraically minus 2 times 2 is minus 4. Minus 2 times minus I is plus 2I. That will be somewhere 4 across to the left and 2 up. That because of that minus sign, for minus 2 times z2, I've rotated z2 180 degrees about the origin. We can see that all of these 3 points are on the same line. Now notice the distance from each of these points from the origin. If we have a constant and we times it by z, if that constant is greater than 1, then your new complex number will be the same direction as z2, but its distance from the origin will be larger. If your scalar is between 0 and 1, your distance from the origin will be smaller, but your new complex number will be in the same direction or same quadrant as your original number. That's like where we have a half of z2. So if our coefficient or our scalar here that we're multiplying our complex number by is negative, we know we rotate 180 degrees. Then we have to adjust the length or distance from the origin depending on the scalar minus 2z2. This is rotated z2 180 degrees. And because of that 2, it's doubled the distance from the origin compared to z2. The last sort of examples I want to look at is what happens if we add 2 complex numbers together on the plane? What happens if we subtract those complex numbers? And what happens if we multiply the complex numbers together? So let's have z1 is 1 plus 2i right here. z2 is 2 minus I right in that fourth quadrant. If I add them together, 1 plus 2i plus 2 minus I, I'll have 1 plus 2, the real parts added, plus, well, 2i minus I is just I. So I have 3 plus I. I'm just going to draw in their distances from the origin and let's see what happens. Notice if you take z1 kind of like a vector and you add on z2 to the end of it, its direction and its distance from the origin, z1 plus z2, indeed kind of like vectors, will lead us to this point that we got above. So addition for complex numbers is really similar to addition to vectors. Let's have z2 this time, subtract z1. Again, algebraically, we'll have 2 minus I minus 1 plus 2i. Let's have a look at where this point ends up. So this time 1 across to the right, 3 down. I'm still in quadrant 4, but I'm all the way further downwards here. Let's bring our distances from the origin back in. Now if I take z2 and I add minus z1 onto the end of it, so opposite direction, rotating 180 degrees, starting at that point z2, again, I end up at this complex number that I got in my answer. So subtraction is also similar to vectors in a sense geometrically. Complex numbers are not vectors, but sometimes they tend to act like them geometrically. z1 times z2, this is my favorite one. So 1 plus 2i times 2 minus I. Remember, complete FOIL will have 1 times 2. plus 2i times 2, I'll do that first, plus 1 times minus I, and then plus 2i times minus I. I'll get 2 plus 4i minus I, and then the last bit, well, I times minus I, that will give me 4 plus 3i. So Z1 plus Z2 is all the way up in this first quadrant, 4 across, 3 up. Now, notice here, if I look at the angles, if I add the angle between Z2 and the real axis, and Z1 and the real axis, if I add these together, I end up with the angle that Z1 times Z2 makes with the x-axis. My moduli, I actually get the moduli of Z1 times the moduli of Z2 together. So in this way, like we know in polar form, when we multiply two complex numbers or more together, we add the arguments and we multiply the moduli to get the new position. So, in summary, each point on an Argand diagram represents a complex number. The complex number z equals a plus bi is situated on the point a, b, where a goes along the real axis, b goes up the imaginary axis. A real number will be located along the horizontal, the real axis, and a completely imaginary number with no real part will be located along the vertical axis. Addition and subtraction. This is similar to vector addition and subtraction, but grab out the lines if you have dotted lines in your exam. Just put the points. You can see that AZ, where A is greater than 1, is in the same direction as Z, just extends its length. BZ, where B is a number between 0 and 1, shrinks it. And because C is less than 0, so the minus part will rotate Z 180 degrees, and depending on what C is, if it's 1, 2, 3, 4, or 5, etc., that will change the length from the origin of CZ. When we multiply by I, we rotate our original number 90 degrees around the origin anti-clockwise. If we multiply by I squared, we just rotate it 90 degrees times 2 around the origin anti-clockwise, or 180 degrees. I cubed will rotate it 90 times 3 times around the origin anti-clockwise, and we just keep going.